What do we know about how our solar system works? We know things move, they spin, circle, and speed through space. We know they grow, shrink, crash, and explode. We even think we know how the solar system formed. And we continue to learn about the remarkable forces and interactions that keep the solar system functioning. First, what's in the solar system? The Sun. Solar means sun. 8 planets, including Earth, orbiting the Sun. A number of dwarf planets such as Pluto. Asteroids and comets. Powerful waves of energy and universal forces. In addition, there are moons, gas, dust, subatomic particles, and more. Our solar system has lots of parts, and they are all tied together by the Sun. Most scientists think the solar system developed about 4.5 billion years ago. It formed near the edge of a group of billions of stars spinning through space called the Milky Way galaxy. Here, a huge swirling cloud of gas and dust, known as a nebula, began contracting. Immediately, another force helped draw the particles into even bigger clumps: gravity. Gravity is an unforeseen force that pulls one object to another. On Earth, for example, gravity pulls an apple from a tree to the ground. While the solar system formed, for hundreds of millions of years, condensation and gravity pulled nebula gas and dust into an ever-tightening sphere. When the sphere contracted to about 1 million times the size of Earth, heat and pressure inside started a chain of nuclear reactions. Our Sun, a new star, exploded to life and began to shine. Some leftover gas and dust remained nearby like debris at a construction site. It formed small, swirling clouds that circled the Sun. The clouds were pushed out by the Sun's nuclear explosions, but at the same time held by its gravity. Eventually, the clouds in space packed together. A vast number of chunks of rock, metal, and ice developed from them. For a while, the solar system became a violent place because of collisions between objects. While sometimes objects were demolished in these collisions, more often the collisions resulted in accretion. Accretion is growth of an object through gradual accumulation of material. Over hundreds of thousands of years, orbit paths got cleared of most materials. They got accreted into planet-sized balls of matter, which were hot and gooey because of heat produced by collisions. But these new planets were too small to cause nuclear fusion, so they cooled to what they are now. Gravity was the major force that pulled the solar system together. Gravity still keeps things tied together today. The law of gravity states that more massive objects create a stronger pull. The Sun has 99% of the solar system's total mass, and its gravity holds the system under its spell. But if gravity pulls the planets towards the Sun, why don't they fall into it? The Sun's heat and other energy waves and streams of particles don't push hard enough to keep heavy planets away. Instead, inertia prevents planets from falling into the sun. Inertia is a natural tendency of an object at rest to remain at rest, and an object in motion to remain in motion. A moving object's inertia keeps it going in a straight line. For example, a ball that is rolled will tend to keep going the direction in which it was rolled. Also, a ball you throw upwards goes straight up and away because of inertia. Eventually, air resistance and gravity will overcome inertia and pull the ball to the ground.
Good engine control on the first stage.
In space, in the absence of air resistance, inertia will allow a spaceship to travel in a straight line forever, unless another force, such as a rocket engine thrust or gravity, changes its direction.
Good chamber pressure and all 3 boosters at the full power on.
With planets, inertia tries to enforce a straight line of travel. Inertia acting alone would send Earth on a path like this, taking our planet farther and farther away from the Sun. But the Sun's gravity gently bends Earth's path. In a remarkable balancing act, inertia and gravity have kept Earth and the other planets in their orbits for billions of years. Planets not only orbit the Sun, they also rotate on their axis. Our planets have been spinning ever since they formed from a spinning nebula that was part of a spinning galaxy. Rotational inertia, another form of inertia, has kept these spinning objects spinning and will continue to do so for billions of years more. Now, let's consider the Sun for a moment. Our Sun is a medium-sized star made mostly of hydrogen gas, like the nebula that formed it. The Sun produces heat and light through nuclear fusion. Deep inside the Sun, immense heat and pressure cause hydrogen atoms to collide so hard they weld or fuse together. The fused hydrogen atoms make a different kind of gas, helium. The new helium atom, however, weighs slightly less than 2 hydrogen atoms before fusion. What happens to the missing tidbit of hydrogen matter? It changes into an amazing amount of energy. In calculating how much energy in joules, the missing mass in kilograms is multiplied by 90 quadrillion. Energy radiates from the Sun as heat, light, and other energy waves. The Sun also blasts out like dust from an explosion a variety of subatomic particles forming the solar wind. The planets can be divided into 2 main groups. There are the inner rocky planets and the outer giants. In addition, the solar system has numerous small pieces, including asteroids, comets, and dwarf planets such as Pluto. The inner rocky planets include Mercury, Venus, Earth, and Mars. All are small and have crusts of rock. These planets are also denser than the outer planets. A bucket full of inner planet weighs about 4 times more than a bucket full of outer planet. The outer planets, Jupiter, Saturn, Uranus, and Neptune, look huge compared to the Rockies. Jupiter's diameter is more than 11 times that of Earth. The outer giants have only a small amount of rock and metal. Instead, they are mostly condensed and frozen gases, especially hydrogen and helium. The arrangement of the two groups of planets is not an accident. Planet formation began with condensation inside the cloud of leftovers orbiting the Sun. Near the Sun, where it is warm, rock and metal particles were able to condense and eventually form planets. However, most other matter, including hydrogen, methane, carbon dioxide, and even water, could not condense. It remained gaseous and drifted farther away like steam from a hot griddle. At about 3 times Earth's distance from the Sun, there is a frost line. Beyond the frost line, it is so cold, under the right conditions, most gases condense. Here, far from the heat of the Sun, gas giants grew in much the same manner as the Rockies, except with condensed gas and ices instead of rock and metal. Separating the inner and outer planets is an unexpectedly wide gap. This space is peppered with countless small rock and metal objects ranging in size from a peanut to big enough to land a space probe on. Scientists think these asteroids might be the remains of a planet that failed to successfully form because of interactions with Jupiter's strong gravity, or are the results of a planet destroyed in a collision. Beyond the farthest planet, Neptune, lies Pluto, a dwarf planet. This cold sphere of ice, rock, and metal travels in a vast region called the Kuiper Belt. Pluto shares the Kuiper Belt with other dwarf planets and millions of smaller objects we call simply Kuiper Belt objects. Somewhere on the far edge of the Kuiper Belt, we meet the heliopause. At the heliopause, the solar wind grows calm. The subatomic particles shooting out from the Sun mingle with and get lost in the haze of subatomic particles of interstellar space. The heliopause marks the boundary of a bubble created in space by the nuclear reactions of the Sun. Still, all of the Sun's power is not totally exhausted. The Sun's gravity reaches beyond the Kuiper Belt and into another vast, mysterious region sometimes called the scattered disk or the Oort cloud. The Oort cloud is home for the last of the solar system's original primordial gases and dusts. Most of these dredges have formed into small ice balls, of which there are billions. They are held weakly by the Sun's incredible gravity, which finally diminishes to insignificance on the outside of the Oort cloud. Once in a while, we Earthlings are reminded of these distant Kuiper Belt and Oort cloud objects. Through collisions or other causes, objects occasionally get knocked into the planet region. We sometimes see the objects as they begin to melt and form comets with long tails reflecting sunlight in dramatic displays. More common shooting stars also may be distant fragments, but they come from the asteroid belt as well. So our solar system has a remarkable number of different parts and pieces tied to the Sun by gravity. But big as it is, our solar system is still just a grain of sand on an immense beach that makes up the Milky Way galaxy, which in turn is surrounded by countless other galaxies in oceans of deep space. Amazingly, the forces that make our solar system work seem to work across it all.